Today, we're talking about molecule shapes. Okay? Molecule shapes are important to the way that they react, the way they behave, their properties, like their boiling points, all that jazz. Okay? So, molecule shapes are determined by what are called electron groups. Electron groups can either be bonds or lone pairs. What's a lone pair? Max?
Two electrons.
There's two electrons in a bond, too. What makes them different? What makes a lone pair different from a bond? Elissa? They're not being shared. They are only on one element, only on one atom. Okay? Electron groups determine what shape, the number of electron groups determine what is called its VSEPR geometry. Okay. VSEPR stands for valence electron shell pair repulsion. Technically, the E and the S are switched, so it's VSEPR, but VSEPR sounds much cooler, so we're going to say VSEPR. So it's valence shell electron pair repulsion. All that means is that electrons repel each other. And since electrons repel each other, it determines how far apart electron groups can get away from each other. And how far apart they can get away from each other is what determines what shape they make. Okay? So I want you guys to think of, let's say, you're at a table at lunch. Okay? It's the last table left, and you are trying to just sit down and eat your lunch, but there's two people that need to sit down, you and someone else. You don't like the other person that has to sit down with you. So are you going to try and sit next to them around this table? No. You're going to try and get as far away as possible, right? Okay. So if there's just two of you at this table, you're going to go about 180 degrees apart, directly apart from each other, right? Okay, this would be the same as electron groups on an atom. They're going to get as far away from each other as possible. So if there are two electron groups, meaning either bonds or lone pairs, they're going to try and get as far apart from each other as possible. Two electron groups would be the linear VSEPR geometry. And we would draw it like this. They get as far apart from each other as they can. So an example of an actual molecule that would have this linear geometry would be our carbon dioxide that we looked at yesterday. Carbon dioxide made this in our drawing. This Lewis dot structure looks like so. If we look at our center atom, there are 2 electron groups coming off of it. Okay, there's 2 sets of bonds that are coming off of it. So those oxygens, or those sets of bonds, are going to get as far away from each other as possible, meaning they're going to go 180 degrees apart. They're going to go into a line. Does that make sense? Questions on that? These first 2 are easy to understand why they make the shapes. Okay, because they're very similar to 2D shapes. Okay. Now if we have 3 electron groups, they make our next VSEPR geometry, which was what? Do we remember the one I showed you? It was a triangle. Did you say platinum? It is called trigonal planar. Okay, trigonal planar is our central atom. I'm actually going to shade in the central atom so you guys know. The central atom with 3 things, 3 electron groups coming off of it. Now this one can also be explained by the table analogy. All 3 of you guys that have to sit at this table now don't like each other for some reason or another. So you're going to try and sit as far away from each other as possible. Okay, in all actuality, that would be 120 degrees apart. Okay, so you're going to sit at equal spacings around the table. Does that make sense? Questions on this one? All right, guys, stop talking. The CH2O that we talked about yesterday would fall under this category. That Lewis dot structure looked like so. In this case, there are 3 groups of bonds, or 3 groups of electrons coming off of our central atom carbon. Since there's 3, they're going to make this trigonal planar shape. Does that make sense? Okay. 4 electron groups. Does anyone remember this one? Tetrahedral. This is where our like lunch table analogy falls apart, because now we are no longer in 2D, we are in 3D. So it'd be like you can sit all around a sphere, up, below, to the side. Okay, So our little table analogy falls apart. However, if you were to get around a sphere, like if I had a floating balloon, just like right here, and someone could levitate, and all four of you guys didn't like each other, you'd get as far apart from each other and the balloon as possible. Okay? To do that, someone would have to go up above the balloon. Okay?
So wait, so there's a hot air balloon and a guy on top.
Oh, okay, on the table.
Yeah.
The guy can't be underneath.
So,
So if someone stood on the table, someone went under the table, someone went outside of the table, then the table analogy still technically works.
yeah, but if someone's eating lunch under a table,
That's
Better than buses.
it makes sense why no one wants to sit with you, you know? Okay,
Who actually do that?
do what?
Either went to the bathroom.
Yeah, but like,
They see one went to the bathroom.
if you see a table that has perfectly good chairs to sit in and you choose to sit under it,
Honestly,
What if you're trying to hide though?
yeah. You're overstanding.
now you're throwing more variables in.
What if you're trying to hide though?
Again, you're throwing more variables in.
Hide?
Yeah. There's nothing wrong with it. I'm just saying,
But see, the
you
table.
won't be surprised if no one wants to sit at the table then.
What if you're hiding from them?
But see, we don't know where people.
See, you guys are making this more complicated than it needs to be.
I'm just saying the table analogy still works.
All right, so we have our central atom, the black one here. In order for them to get as far apart from each other as possible, they can no longer be in a 2D plane. They can no longer be flat. Okay? So, what happens is they will get that little triangle down here on the bottom, and then one person is going to be up top. The triangle here on the bottom is not flat. Okay? It's sort of like a pyramid, like so. Okay? The bottom part is like a pyramid, and then there's another person coming up top. Okay? So we are now in 3D form. Yes. I mean, like you could shift it to where it's like this now, and now you have two people coming diagonally out of the top and two people coming diagonally out of the bottom. But the way it's mostly drawn is like this, and they're technically as far like they're equidistant apart from each other, but it looks like there's one up top, three on bottom, like that. Yeah. Yeah. Okay. I'm going to show you guys how chemists officially draw in 3D. Okay. So, if we are drawing something in 3D, we have our central atom here. If something is coming out of the plane of the board, meaning it would be coming from the sheet out towards you guys, we use a wedge to draw it. Normally we would draw a line like we did up here with the trigonal planar, but if it's coming out of the plane that you're looking at, it will be a wedge. Okay, so this would be like if I'm holding the tetrahedral like this, you have one coming out towards you, you have one that's going back away from you, and then you'd have two that are in the plane of the board. Okay? So this first one would be the one with the wedge that is coming out towards you. Does that make sense? Okay. The one that is going back away from you will be dotted. It's a dotted line. So that's the one that's going away from you. Now, when I look at this tetrahedral, I can get 3 of the atoms, including the central one, in the same plane. Like if I took a piece of paper and tried to cut this thing in half, trying to get as many atoms as I could get 3 of them, including the central one. Okay, and so those, I would have 2 regular lines that are in the plane of the board. Okay, so these 3 would be the ones that are in the plane of the board. This one in the back is the dotted line, and this one is the one coming forward towards you guys. Does that make sense? Okay. Example of this one. Methane, CH4. Its Lewis dot structure would look like this. Questions on tetrahedral?
Wouldn't there have to be like a triangle thing on that? Like the wedge?
Oh, for this?
Yeah.
This is how we would write it in 2D.
Oh, okay.
If I was writing it in 3D, I would draw it like that.
Okay, sorry.
Does that make sense?
Yeah.
Okay. Okay, so I'm showing you guys just the regular formula, the 2D, and then the 3D. Okay? Any other questions before we move on to the 5th group? Or I guess 5 electron groups. Okay. Oops. 5 electron groups. This one is the double triangle pyramid. This is called trigonal bipyramidal. So if you look straight up and down at this, like from a bird's eye view, you see a triangle, right? So this triangle is sort of the middle part of this 3D shape. And then if I flip it around this way, you see the top and the bottom of the molecule. Okay, so you have your top and bottom, and then 3 around the center. Does that make sense? Yeah, nay? Top, bottom, 3 around the center. I'm getting like 0 confirmation from you guys whether you understand it or not. So
I'm trying to draw.
I was about to get to it.
Sorry. I wanted to try it all.
I appreciate that, Max. Okay. So this one, the trigonal bipyramidal, if I try and do the little paper thing, getting as many atoms as I can in the same piece of paper, I can get 3 of them and then the center atom. I can get this one, this one, this one, and then the center atom. Okay? So you should have 3 regular lines coming off of the central atom, 1 coming out towards you, and 1 coming out this way. Okay? So that would look like our central atom. Regular line, regular line, regular line, wedge coming out towards you, and then dotted line going out behind.
Oh, they're only 3 far.
Yep. I don't know an example of one off the top of my head. I think it's SF5, so we're just going to go with that one. SF5 would have 5 things coming off the central atom. 2, 3, 4, 5. So it'd be like that. I would actually probably make this a little bit more angled. Yeah. I guess if I do this completely correctly, it would have the lone pairs on each of the fluorines too.
Wait, doesn't that mean S has like 10 valence?
Yep. Everything we've talked about so far has exceptions to it. So the octet rule, more like a guideline.
Oh, great.
Octet rule is more like a guideline.
With just this or with everything?
With some things.
Wait, what did he list his name?
What?
What did he list his name?
It would mean that sulfur has extra valence electrons. It doesn't, but we'll figure out what to do with it later. The steps still stand. The steps still stand. Yeah.
So that wouldn't be like completely done.
This one would be completely done.
What?
Yeah.
But then it has extra.
Yeah. So the S violates the octet rule.
But only S.
No. Only this S.
Only sulfur.
Only specifically this one.
Oh, okay. So this is just special.
Yeah.
But usually it'd be okay.
Yeah.
Are there others like this?
Yeah.
How do we know if we're doing it wrong or if it's special?
If you can, the general idea is you make as many things follow the octet rule as you can. In this case, all of the fluorines, all 5 of them follow the octet rule. It's only the sulfur that doesn't.
Will this be on a test?
Yeah.
Will you tell us? If it's
Not the test coming up. It'll be on a test for next semester.
Will you tell us if it's special? We gotta
All right. Questions on trigonal bipyramidal?
9.
Okay. Final one. Six electron groups. You guys remember what this one was? Octahedral.
Is there anything that goes past 6?
Probably somewhere, but I don't know of any. Octahedral. Listen up. Octahedral has 6 things coming off the central atom. So if I have my central atom, if I do my piece of paper, getting as many atoms as I can get 4 atoms in the central one. And get this one, this one, this one, and this one in the same piece of paper. This one will be coming directly out towards you guys. And then the other one back here is coming out the back side.
Yeah, that's how I accidentally do 5
well, you're just step ahead. So I can get 4 regular dots or regular lines, 1 dotted one going back, and 1 wedge going forward. This is an octahedral. Bless you.
And see, this one actually makes sense to my head. The bottom one is confusing.
Yeah.
It's just weird.
This one, it doesn't really matter which one you look at. It has the same shape all the way around.
Yeah, I think that's why I can visualize it in my head better.
This would be your typical diamond shape.
Typical what?
Diamond shape.
Oh.
Okay. An example of this one would be the gas that makes your voice really low, sulfur hexafluoride.
Helium makes it fly high.
I think it would work because
Whoops.
I guess there's 6 of them.
Yeah. Okay. Oh, whoops. Scroll up a little bit. These are our VSEPR geometries. Now, if I'm giving it a name, what does that tell you?
it's important.
It's important and remember it and
Beyond the text.
why wouldn't I not just call them geometries?
Because there's more than one kind of geometry.
It's different from math.
There's more than one classification of geometry
In this or in general?
in general.
Okay, I was about to say.
Are we learning the other one?
Yep,
Oh.
but not today and not tomorrow.
What are we doing tomorrow?
Tomorrow is practice with Lewis dot structures and VSEPR geometries. Okay. It will be recorded just like this one was.
Okay.